Hey, welcome everybody on this hot and smoky day here in Michigan, and we're glad you could join us. And I'm John Sarver with Great Lakes Renewable Energy Association, hosting this Thursday evening Zoom that we do every Thursday, most Thursdays on clean energy topics, a lot of solar stories. But first, I need to thank our sponsors, the State Department of Environment, Great Lakes and Energy, Eagle. Homeland Solar, Harvest Solar, Shree Energy, and Sumter Solar. We appreciate their support that enables us to do this and other sorts of educational programs. Tonight, we got a really interesting topic. Dr. Parth Vaishnav, who's an assistant professor of sustainable systems at the U of M, has been working in the area of V2H, vehicle to home systems. And so he's come here tonight to kind of share what they're up to and what they're learning. Parth, thank you for joining us. And you may want to start by just giving us a little about your background and experience.
Sure. So my name is Parth Vaishnav. Thank you very much for giving me the opportunity to join you all this evening. My apologies for being a bit late. My work computer is managed by the university, and there was some rule apparently which said that it had to update at precisely 7 o'clock this evening. So it was set to restart. So I just scrambled and found another computer, and I think we're in good shape now. My background, I'm a mechanical engineer by training. I got my PhD in a program called Engineering and Public Policy at Carnegie Mellon. And the goal of that program is to train people to work on policy issues where you can't ignore the technical details. So it's often people with an engineering background who then apply that engineering background to policy issues. And that's basically the kind of work I do. I focus on vehicle and building electrification, and try to understand the benefits and costs of those things and how those things interact with each other. Um, yeah, there was a question about being able to retrofit a battery and whether vehicle batteries can be used. So that, John, as you said, that really is the topic of what I'm going to talk about today. Um, and so uh, I'm happy to kind of get started on the topic. I'll try to wrap up in 20-25 minutes so that we have plenty of time for questions. Um, I will just um share screen. This is always a bit of a dance with Zoom, but hopefully uh, that should work. Okay. I hope everyone is seeing
Yes,
the right screen now. Okay.
yes.
Yeah. So this was research that actually was led by one of my graduate students who's now graduated, Jiahui Chen, now Dr. Jiahui Chen, and a group of colleagues from the University of Michigan and from the Ford Motor Company. And this research was actually supported by funds from Ford. Um, and so the question that we were trying to answer is, how do electric vehicles interact with other sectors? Can electric vehicles make it cheaper for you to electrify your home in other ways? So if you wanted to adopt a heat pump instead of using a gas furnace for heating, does the fact that you have a heat pump make it cheaper for you to own an EV and vice versa? And a second part of this study was to find out whether for the electricity grid, for the electricity system, whether the presence of electric vehicles made it cheaper to add renewables to the grid. And the genesis of this was this kind of landmark study that came out now 7 or 8 years ago, which argued that if we wanted to get greenhouse gas emissions down to zero, there were certain sectors where it was easy to do. So things like the residential and commercial sector was easy to decarbonize because What you had to do was switch everything to electricity and then use clean electricity, and then you were done. Um, Short haul transportation, so things like passenger cars, light trucks, medium duty vehicles, also easy because you could electrify them and use clean electricity. What was hard to electrify was load following electricity. So this is uh, electricity generation that kind of ramps up when you need power and ramps down when you stop needing the power. And because you can't get the sun to shine uh, a bit brighter when you turn on your EV charger or your dryer or something, um, typically renewables by themselves are not good sources of load following energy. You need to do something else, and these folks concluded that this was hard to decarbonize. And so the question was, given this, can electric vehicles help? And this is actually, in fact, the same question that was asked before. Can you use the electric vehicle's battery with uh, uh, to actually help make the grid cleaner, including using your own solar panels better? Um, Now, the idea is to use electric vehicles as a resource for the grid rather than as a burden. And there are different ways in which you can charge an electric vehicle. And I'm just going to define some of the terminology here. So our baseline assumption is that people do what is called uncontrolled charging, which is that if you think that the battery of your vehicle is below a certain threshold, um, 20, 30, 40%. You just plug it in whenever you get home. Control charging is you plug your electric vehicle in whenever it is going to be stationary for a while, whether at home or at work. And then the grid decides when to supply energy to the vehicle subject to certain rules. And one of those rules is that the vehicle should always be ready to provide you with the mobility that you need. So you shouldn't have to change how you use the car to drive. Vehicle to home is a two-directional flow of energy. So here we assume that the house has a choice. The house can either get electricity from the vehicle's battery for some of its uses, or it can get electricity from the grid. And there's a charger in the house which facilitates this. And any charging of the vehicle occurs through that charger. In this construct, there is no direct interaction between the vehicle and the grid. Everything goes through the house. At no point do you extract energy from the vehicle's battery to feed it into the electricity grid. That's not allowed to happen. And then vehicle to grid is where you kind of make the home irrelevant. Uh, Over here, the vehicle can directly interact with the electricity grid. You can supply power to the grid and you can charge using power from the grid, from the electric vehicle battery. So with that, the first question that we tried to answer was that are there synergies between electrifying homes and electrifying vehicles? Uh, and we ran, to answer that question, we ran a bunch of optimizations. And we ran that for the combination of scenarios that was described here. So we assumed that we ran this for individual cars in 432 different locations in the US. Those locations were defined by differences in the electricity system, which is different in different parts of the US, and the weather, which determines how much energy the house uses and actually how much energy the vehicle uses also to travel a given distance. So for each of those regions, we modeled 15 vehicles, and for each of those vehicles, we ran an optimization uh, where, in one case, we basically said that actually you don't need to optimize anything. If your state of charge is below a certain level, just charge to 80% the first chance you get. In a second optimization, we said minimize the cost of charging the vehicle. You have 2 weeks foresight of what the vehicle is going to do and what the grid is going to do. And the optimization is constrained by saying that the vehicle's driving needs will always be met. You don't have a situation where you can say that I actually want to drive somewhere, but I'm discharging to the house or something like that, or I don't have enough electricity and so I can't go. You always have to be able to drive. And then we ran what we call a V28 scenario. And in this, the optimization was that you must minimize the cost of all household electricity. I've kind of deliberately canceled any reference to greenhouse gas emissions here. We're optimizing purely on cost over here. Um, the assumption is that you have, again, 2 weeks foresight, driving needs are always met, and the home's electricity needs are always met. In the V28 scenario, like I said, the home decides whether it wants to take power from the vehicle's battery or from the grid. And if in a particular hour the home takes energy from the vehicle's battery, that energy has to be made up for in some other hour. And we ran this scenario for a home that has baseline heating, which in most places is natural gas, in some places is baseboard heating, um, and an alternative scenario where all the heating was provided by an electric heat pump. Of course, for controlled and uncontrolled charging, it doesn't matter what kind of heating you have at home. And so we kind of didn't run, we only ran this scenario uh, for the baseline home. This is kind of the details of the methods that we ran, and these are results. So the headline number is that if you have vehicle to home, and either you or an energy service provider uh, is subject to the wholesale electricity prices. So you're allowed to buy electricity when it is cheap on the wholesale market, and avoid buying electricity when it's expensive on the wholesale market. Then, compared to uncontrolled charging, using V2H will save you on average around $2,000. There are places where it won't save you very much money. It'll save you very little money in Vermont because Vermont is 100% renewable. And so there isn't a lot of variation in the price of electricity. And it'll save you quite a lot of, and it'll save you more money in places like Texas and California, where there's quite a lot of renewables, but there are also hours when you have fossil fuel usage. So there's a lot of value to shifting consumption from when you have fossil fuels at the margin to shifting it when you have renewables at the margin. And this is not a matter of producing a benefit just because you're deciding when to charge. Even compared to controlled charging, there is a benefit associated with V2H because now you're actually deciding when to buy energy for all your house's consumption, not just for the electric vehicle. We also found that there are uh, uh, there are relatively small synergies between having an electric vehicle and a heat pump. So you save a bit more money if you have an electric heat pump versus if you don't, if you do V2H. And there are parts of California and Texas, and these are the two plots that you want to look at here. Let me use this laser pointer. These are the two plots you want to look at over here. There are parts of California and Texas where the savings that you achieve from changing when you buy electricity are so large that they completely offset the cost of charging. So in effect, you're charging for free. And then this plot kind of makes the point that I made before, which is that there's a little bit of synergy if you have an electric heat pump because you're just moving around more electricity. We also find that in these parts of the country where it's blue, um, using vehicle to home can cut life cycle greenhouse gas emissions from electricity use relative to a no EV counterfactual. So because you're purchasing electricity for the vehicle itself and for your other uses, at times when electricity is cheap, you're not even optimizing for greenhouse gas emissions, but electricity tends to be cheap when it is clean because the marginal cost of solar and wind is low. Because you're doing that, your greenhouse gas emissions are lower than they would have been had there been no electric vehicle at all. So you're offsetting the emissions associated with charging, and you're in the parts where these plots are blue, you're actually offsetting the emissions associated with even producing the vehicle. Um, for about 70% of the counties in the country, where 62% of the population lives, um, you actually eliminate emissions uh, from charging. So your charging emissions go down to zero. You don't reduce your emissions so much that you also offset the emissions associated with making the vehicle, but your charging emissions are either zero or lower for about 60% of the population if they do V2H. And this shows the reduction in emissions relative to uncontrolled charging. Um, Relative to uncontrolled charging, you reduce emissions by about 30 tons over the life cycle of a single vehicle. So that's an enormous reduction in emissions. And again, even in terms of emissions reductions, there is a slight synergy. You do a bit better if you already have a heat pump and you do V2H with the heat pump. And so our conclusions were that V2H is low-hanging fruit to cut EV charging emissions. Uh, you can cut EV charging costs. In some cases, you can eliminate EV charging costs if owners are exposed to these wholesale prices. And you can do this through an aggregator. There are companies like ViewGrid that will do this. And our assumption is that some or all of that benefit is passed on to you. Um, for about 60% of the population, if they did V2H, that would eliminate emissions associated with charging. There are synergies between vehicle and heating electrification. And I didn't show the results for this, but you actually cycle the battery a lot more than you otherwise would if you do V2H. You cycle it 2 to 3 times more. And we tried to simulate what the effect would be on battery degradation. And we ran a whole bunch of different models. And what we found was that V2H didn't produce a whole lot of additional degradation. So at the end of 15 years, you had 2, 3, 4 percentage points more degradation than you would have had if you weren't doing V2H. So that means if your battery at the end of 15 years was going to degrade by, I don't know, 25%, then it would degrade by 27% instead, or 28% instead. Um, Now, what we did not quantify, and which actually may matter to a lot of people, is that you can use V2H as backup power. We've just quantified the benefit of V2H as a price arbitrage tool, but you can use it as backup power. This is quite expensive, but this can become cheaper. The reason it's expensive today is because the batteries produce DC power, our houses use AC power, and so you need a converter that converts that DC to AC. But in fact, level 2 chargers, if you go to a charge point charger, is AC and the motors are AC. That means the vehicle has DC AC converters. It's just that you can't use them to get power for your house. And this is starting to change, where manufacturers are in the process of building vehicles where you have access to the vehicle's DC AC converter. And so the device that you have to install in your house is a much simpler, much less expensive device, which a less experienced electrician can install. And so if this happens, then uh, taking power off your battery will become a lot easier. And so, yeah, like I said, the study was sponsored by Ford and actually internally by the School for Environment and Sustainability at the University of Michigan. There's a QR code which should let you download the study. If it's behind a paywall, email me and I'll get you a copy of the study if you'd like to learn more. Um, and so I'll dive into a second study. I'll go through this in 5 or 6 minutes. This takes the perspective of the electricity grid, not a single household. And the idea here was to answer the following question: that um, as you add electric vehicles to the grid, um, if those vehicles can actually interact with the grid, if they can buy surplus power from the grid when there's too much power on the grid and then sell it back when there's too little power on the grid, can their ability to do that make it easier to add renewables onto the grid? And so this kind of uh, is a cartoon version of the modeling that we did. Uh, Basically, as you add more and more solar and wind capacity to the electricity grid, the aggregate cost increases, um, but also the aggregate revenue increases. But you get to a point where the revenue increase starts to flatten because the electricity is being produced at times when demand is met, and so then that electricity has to be curtailed. You can't sell it, and if you actually produce too much, then you can start to create negative prices, and your revenue actually starts to fall a little. And so what we did was we ran this analysis for different levels of aggregate wind and solar capacity. And we ran it for three scenarios. One, where there were no electric vehicles on the grid. Um, a second scenario where there were electric vehicles, but they charged as they wanted. A third scenario where there were electric vehicles, but you could control when they charged. And I'm sorry, a fourth scenario where you had vehicle to grid, where those vehicles could actually absorb extra energy if the renewables produce them. And this plot kind of summarizes what we found. We ran this for the PJM region, which is the electricity market in the northeast of the country. We kind of made some standard assumptions about what is already installed in PJM, what is going to be installed, what is going to retire, and how the rest of the demand in PJM is going to evolve. And then given that we knew what the power system looked like, we looked at how it would be dispatched as you added more and more renewables to it. And so this black line is the annualized cost of wind and solar as you add more and more to it. And the colored lines that kind of run across that are more or less horizontal tell you what the revenues from that wind and solar are. And at the point at which these lines intersect, that tells you the maximum amount of renewables that you can install in that scenario. Because at that point, the cost and revenue are equal. And if you install more, your costs exceed revenue, and you're not going to make any money on them. So you wouldn't install them. And so what we see here is that if you don't have any plug-in electric vehicles, PEVs, then uh, it's optimal to have 64 gigawatts of renewables in PJM. If you have vehicles but with charging, you get pretty much the same answer. By and large, because most vehicles don't charge when the sun is shining. Um, and secondly, if you could control when the vehicle's charged, you could actually get a bit more renewables profitably, but not a whole lot more. But if you set it up so that the vehicles could absorb this energy, so they could store it in their batteries when there was excess production, and then supply it back after the sunset or when the wind stopped blowing, then it became profitable to add a whole lot more renewable onto the electricity grid. Um, and if you kind of work out what happens here, you want to look at this part of the graph, if you have uncontrolled charging, most of that additional demand is met by combined cycle natural gas. If you have controlled charging, then there's some additional wind and solar. There's a little bit of additional coal. You're mostly getting rid of fast ramping gas turbine because the batteries in the car are doing the work that the fast ramping gas turbine would have done. But if you have V2G, you're getting rid of a lot of combined cycle natural gas and replacing it with wind and solar and a little bit of coal. I think this has to do with the fact that coal, at least in this simulation, was the cheapest load following source of electricity. And if you quantify the effect of doing this in terms of avoided mortality, um, this is this is the change in the damages done from the pollution associated with power production. Uncontrolled charging increases pollution, by about a couple of $100 million or about $100 million in 2035. Um, Control charging reduces it by a little bit, again by $100 million. But if you do V2G, you reduce damages from premature mortality and global warming to the tune of about $800 million in that year. So there's an enormous benefit in terms of avoided pollution and avoided greenhouse gas emissions. And so, I mean, what we learned from this is that if you have uh, if you have vehicle to grid and you have control and you can control when you charge and discharge, uh, that can have negative consequential emissions. So you're actually adding a load to the grid, you're generating more power, but the net effect on the grid is that it is emitting less than it would have otherwise. Um, and so there are some limitations, but we think the broad point is pretty robust. And again, this study is published also. This is a QR code. Um, and at about the same time that we published this study, another group which actually contained one of our colleagues who's a co-author on this study, published another study which showed that even if you don't do V2G, uh, the the kind of long run emissions from the power system uh, fall quite a lot just because you've added electric vehicles and changed the shape of the load on the electricity grid. So the because today wind and solar are the cheapest way to add power to the electricity grid, if you add additional sources of demand on the grid, then the effect of that is that you can actually reduce grid emissions if those sources are somewhat flexible. Uh, I think that's all I've got. That was about 25 or so minutes. So very happy to take questions.
Hey, thank you, Parth. Why don't you stop the screen sharing? It'll be easier for us to see folks.
Yeah,
As
absolutely.
most of the participants know, we have virtual hands. It makes it easier to kind of see who's asking the question. So the first question goes to John Gorley.
Yeah, thanks, John. Uh, this is a practical question, Parth. Are there any vehicles and chargers and utilities where you could actually implement this this is regarding your first study, where you could actually implement the optimization that you're seeing in the real world? Is there any real equipment that will let you do this?
So there is equipment. Um, it is in terms of whether anyone is doing it, I think the answer today is almost no one. But not Ford, but GM just announced a partnership with Weave which I think will start to do this kind of thing. So the study is somewhat forward-looking, but I don't think it's completely pie in the sky. I think in the next couple of years, you'll start to see announcements where this kind of thing is done. There are vehicles which will let you use power for backup, and I think for backup, both GM and Ford have solutions which will sort of automatically switch to your truck battery or whatever to, if you have a Ford F-150 Lightning or a Silverado or something, it'll switch to those batteries if you have an outage. And Ford ran a trial with Baltimore Gas and Electric a couple of years ago where the utility paid you if you connected your Ford F-150 Lightning to your house between 5 and 9 on weekdays and permitted the house to buy some electricity or get some electricity from the battery rather than buying it from the grid. And I think the utility paid you quite a lot if you agreed for your truck to be used in that way. I don't know that a lot of people signed up for it, but uh, it is it is on the cusp of becoming a practical proposition.
In they did that in Baltimore. What about in Michigan? Do either of the big utilities or do any of the utilities provide the arbitrage information you'd need to do this properly?
So the arbitrage information is publicly available. You could go on gridstatus.io right now and look at what the day ahead price or the hour ahead price in different parts of the country. So that is a public market, and you can track the prices. And this is the bread and butter of electricity traders, so they have the ability to predict and so on. So that infrastructure is there. It's the physical infrastructure of actually doing it that isn't necessarily there.
But I can't buy electricity at uh, the price that you're talking about. I have to pay what what DTE wants to charge me. So
Correct. Correct. So I think right now we don't have a rate structure that lets you do this, which is why the way we described it was that there would be an intermediary who would do this for you. But there are places, Texas, and it turns out Chicago, for example, where you can sign on to a rate where you're just exposed to the market structure. You pay a different price for electricity every hour of the day, every hour of the year. And so it is possible to do this. But as we know from the 2021 outages in Texas, that also meant that people got bills that completely wiped them out. So what we're assuming is that there would be a middleman who would be sophisticated enough to hedge that risk, who would then share the spoils with you.
okay. Well,
Yeah.
thanks.
Go ahead, John Richter.
Sorry, it took me a second there. Yeah, I'm also interested in the practical, applications of when you can do this. So, I have one of the vehicles that I can run some load off of, but it's 120, right? Not 240, so I can't kind of feed it into my main breaker. And from what research I've done, I mean, yeah, Ford and GM both have systems where you can use your vehicle for backup power, right? But they're proprietary and they're expensive. I'm seeing prices in, six, eight, $10,000 for just the
Yes.
equipment, right, to enable that capability. And you talked about that a bit, right? How we could bring that down with some different design. Um, but I will point out that I mean you can do full vehicle to home kind of manually with that. If you wait till the sun goes down, you just flip off your main breaker. Your car will think that you're having a power outage, and it will run your whole house.
Yep.
Um, and that's what I would love to do. But I haven't seen the systems out there that'll really do it. DTE is doing some kind of pilot with Ford and or GM. I can't remember. Um, but I don't have a lot of faith that the utilities are going to help us get here because they really don't want anything owned by somebody else to be reducing their peak demand because they make profits by meeting peak demand by building more power plants. So I think we're going to have to do this in spite of the utilities, not with their assistance and blessing.
There is nothing there that I disagree with, except to say that um, the AC vehicle to grid that I talked about, where you have an inverter, where you access the vehicle's onboard inverter, because depending on the vehicle's architecture, uh, y- you are the vehicle is using more than 240 volts of AC power to drive its motors. And so it's a question of having an inverter that lets you tap into the vehicle's ability to do that, to convert the battery's DC energy into AC. Um, and
Well, that's something I don't know. Like, what AC voltage do EV motors run on, right? I know my EV's battery bank is 800 volts of DC, but I have no idea what actually is going to the motors.
yeah, so I don't know off the top of my head also, but the ability to at least take 240 volts of power is uh, I don't know that it's that distant.
This is Jens. I work on these motors and stuff. I mean, the voltage the inverter delivers to the traction machine is relative to the power you need. So
That's right.
if you
That's
go on
right. That's
slow
right.
over the parking lot, it'll be very low. If you
That's right.
stomp it, it'll be near the bed. Or if you're towing up a steep hill, it'll be close to the battery voltage. And then
That
some of them even have some buck boost systems that boost it up even higher than the battery.
that's right. So yeah, if you have one of the Kia or Hyundai vehicles, then yes, you have the 800 volt architecture, and I assume that the motors can operate up to those voltages, and then it is kind of metered.
Go ahead, John Freeman.
I have two quick comments. The first one is disappointing. There's an article in today in the New York Times. I think it's on the iPad version, which is a couple of days ahead of the print version, that talks about the state of the electric vehicle of General Motors, Ford, and Stellantis. And it's a pretty dismal picture.
It
So I
is.
find it ironic that Ford Motor Company, I think it's great that Ford Motor Company funded this study, but at the same time, I don't think they produce the 150 Lightnings anymore. I think they've gotten out of it because of the loss of the, tax credit because of Trump. And I don't even think General Motors is doing a whole lot. And of course, the car companies that probably are thinking along these lines, like BWD out of China, they can't get into America. So I'm a little concerned about whether the automobile industry is really thinking forward, or as usual, they're thinking about the next quarter, profits or what they have to report to Wall Street. But that's not my question. The other practical area that Richter didn't talk about is that this fall, that both DTE and consumers are going to file their integrated resource plans on how they plan on building capacity for the next 5 to 10 to 15 years. So I think this is an opportunity to talk about vehicle to grid or vehicle to home and how we can displace the need for more peaker power plants if we in fact implement what you are talking about, Parth. And so what I want to ask you is whether you would be willing to work with us, maybe to see what General Motors and Ford or what DTE and consumers are proposing, and whether we could challenge them on some of their assumptions, because just like Mr. Richter said, they probably are trying to stack the deck against this technology, whereas your study shows that, in fact, it can provide some really nifty benefits. So, would you be willing to help us, is my question.
Yeah, absolutely. Yes, and I seem to remember a rate case where I think the Public Service Commission pushed back on consumers, I think it was, and said that, look, you have to account for the possibility of using virtual power plants in making your rate case and in your IRP. So yes, so the short answer is yes. I'd be happy to I'd be happy to help, and they ought to account for the fact that some of this is possible without a huge amount of investment on their part.
Great, thank you.
Hey, Parth, I was a little surprised at your conclusion that greater use of batteries for like home use didn't have much of an impact on the battery capacity over time. I've kind of always assumed that if a battery cycles more back and forth, that it affects the life of the battery. Uh, and I assume that's what you're also talking about when you were talking about the capacity isn't reduced that much. Could you kind of explain that a little more?
Yeah, so I should first add all the health warnings that go with that. The first is that it's based on public models, and those public models are trained on single cells, and we don't know. We know that they're NMC cells, but we don't know the exact chemistry of those cells. And a lot of degradation and damage occurs because of voltage differences between cells. You don't know how the person is driving it. And so it is possible that we miss something. Having said that, there are a couple of things that I think make our conclusions more robust. One is we ran this for a whole bunch of different models. We didn't run it for one model. We ran it for a bunch of different models. And we always found that regardless of how much absolute degradation the model predicted, the difference between V2H and uncontrolled charging was never that large. And there are a couple of explanations for that. The first thing is that newer chemistries don't have cycling as the dominant degradation mechanism. The dominant degradation mechanism for some of the newer chemistries is what we call calendar aging, which is it effectively sits there and rusts. Like it's literally a form of rusting that's happening. And so that actually is just dependent on state of charge. So if it is very highly charged, and the passage of time, and is not sensitive to cycling. So that's one thing. And the second thing is you are cycling them, and in the aggregate, there are a lot of cycles, but there are two sort of mitigating factors. The first is that you're also reducing the average state of charge of the battery, which helps with the calendar aging. And the second thing is that you're cycling them extremely gently. Your home is unlikely to pull more than 2 or 3 kilowatts. Uh, if you if you twitch your if you twitch your foot while you're driving, you're probably changing the amount of power that's being supplied by that much. So this is extremely gentle cycling. The C rate is really, really low. And that also means that even though when you add it all up, there are a lot of cycles, they're very, very gentle cycles. So our guess is that for all those reasons, uh, cumulatively, you aren't doing a lot of harm to the battery. And the chemistries have gotten better. Most of this is based on NMC. LFP is almost completely immune to cycling, lithium iron phosphate.
Thank you. Jens, go ahead.
Yeah, on that second study that kind of assumed managed charging, uh, basically any time through the week or something. does that imply it's plugged in when I'm at work, or how did you account for the vehicle not being home? And actually, the same applies for like if the vehicle is supposed to help with the air conditioner, how 8 hours, 9 hours a day I'm not home. Was that accounted for in that first study?
Yeah, so for the control charging simulation, in the first study, we assumed that the vehicle had to be stationary for 8 continuous hours. And for control charging, it could be either at home or at work. For V2H, of course, it has to be at home. So it's fairly conservative, and I think for the V2G, we didn't control for where the vehicle was, but I think we have this conservative threshold that it has to be stationary for 8 hours, and the vehicle use profiles are simulated, and there's typically only a couple of places where the vehicle is going to spend 8 hours, and that is work or home. So I think the short answer is we've assumed in the first study that V2H can only take place at home, but V2G and control charging can take place at home or at work.
Yeah, I think that plugged in at work, I think, is indicates that there should be effort to get plugs at work and plenty of them, so the cars can sit and wait for the sun to come at lunch. Because right now most workplaces have like, if any, like a couple of chargers, and they get fought over, and they get cranked up to full tilt as soon as you get there. So that's something, policies and things can probably address to help the employers like work it out. Not for you, but for the rest of the audience.
No, 100%. And there's been a couple of studies which, even if you're not interested in V2X, then just from an emissions point of view and grid economics point of view, it's optimal to charge in the middle of the day, because across the US now solar is so cheap and there's so much solar that you really do want to put loads in the middle of the day, and that implies workplace charging.
Yeah, I've listened to a few podcasts and studies that kind of contrast the intense desire to make these fast chargers everywhere, great expense, great grid load, and some suggest just put plugs everywhere, like put them all at the work, put them all at the apartment, just keep the freaking thing plugged in, and then let it charge when the energy is there. It's a better deal, but well, anyways. That's just a side note here.
Yeah, no, I completely agree. We've got 3 hands up. Peter Colvus.
Hi.
John Sarver, you're on mute.
I guess my question is whether there's been any consideration or comparison of the vehicle to grid case versus simply a grid scale battery, cited by the power company, or even virtual power plants based on home batteries, especially for the economics.
Yeah, so I think the answer is partially yes. So as a sensitivity to that paper, we assumed that there were a whole bunch of stationary batteries as well. And of course, it's better to have a stationary battery because it's available all the time. But we've assumed that the EV battery is free, that it's already there, and the stationary battery is going to cost you something. What we haven't done is to actually do an analysis of the cost of controlling all these vehicles and the uncertainty that you'll have access to them versus just putting a whole bunch of batteries in the grid. I've presented this several times now, and that question always comes up where people say that, yeah, but batteries are cheap and getting cheaper. Why would I bother with all this? And yeah, that's an open question. I've also heard that, look, it's 5 to 6 times cheaper for me to get access to an EV's battery than to install it myself. But I haven't done the analysis and I haven't seen numbers. This is coffee talk during conferences.
Okay,
Sorry, just as a quick follow-up, you said that you're assuming the EV battery is available when the electronics to the charging equipment, as Phillips mentioned, is quite expensive. So that's something that has to come into the analysis.
Yes, and to some extent, the way we framed our analysis was that this is the most that the charging equipment can cost. So, if it's going to cost you $12,000, someone might want it as backup because it's cheaper than a whole home generator, but it doesn't make sense from an energy arbitrage perspective. But if it's going to cost you $2,000 or $1,000, which is possible if you have AC V2G, where you're using the inverter that's already on the vehicle, then this becomes an attractive proposition.
Jay, go ahead.
I see no desire whatsoever to help out the grid, nor provide any power to the grid at any time for any reason. If you've got the power, keep it in house, use it locally, store it locally, and never have to worry about them. That's paid off well for me, particularly in this last storm. But what I know some hackers are doing is they're taking the off the NACS connector on the EV. They're grabbing the DC pins on that. They're convincing the car to enable that at anywhere from 400 to 500 volts direct from their battery. They're feeding that into an MPPT charge controller on the input of their home solar system. Of course, that will take up to, in most cases, up to 500 volts and simply run your home, run your inverter, whether you're on grid or not, and will also charge your battery, your 48-volt battery bank. That seems incredibly efficient with only about a 2% loss through the MPPT. It's also, I think, a lot safer. Having to go and run off the car, get an inverter that then goes and matches my existing inverter and or the grid just seems like a lot of price, a lot of cost, a lot of complexity, and a lot of hardware you're paying for that you only use occasionally. Take the car, let it feed the input of an MPPT that's already there, and your system runs fine. Is that something you guys are experimenting with? I know hackers are doing this, but are you guys working on something like that?
Uh, we are not. So again, these are not lab studies. Uh, Again, I think to some extent the AC V2G solves some of that problem because you have a traction inverter that is doing all this in the car. The question is whether you want to make it bidirectional.
Clifton Brown, go ahead.
Yeah, a question. In some of the conversations, what I thought I heard is you would charge the car for cheaper electricity when the sun was out. But at least in Michigan, with our dual rate structure, the rates go up during the day, not down. So did I mishear?
Yes, you didn't miss here, and you're absolutely right. But what we did assume is that you were subject to the wholesale rates of electricity and not the retail rates. Uh, the this wouldn't work as well with retail rates. Somewhere in the appendices of our paper, we did run this with DTE's retail rates, and you actually can save some money, but you do it in a way where you actually increase or keep level your greenhouse gas emissions because then the incentive is is to charge overnight and then discharge from 3 to 7 or 11 to 7, depending on what rate you're in. So,
Okay, because what I do now to charge my EV is obviously charge it at the lower night rates, or my night rate goes up to 2 p.m., make sure I've got sun and push sun into the battery instead of back to the grid. But that's
uh,
to me that I'm able to load shift and charge shift some, but it's all manual.
right, right. Our assumption here is that the person who or the entity that does this is exposed to the wholesale rates, not to the retail
But how
rates.
practical is that? I mean, the typical homeowner or typical EV owner, they, correct me if I'm wrong, they don't have access to the wholesale market. They deal with the retail market.
So they don't in Michigan. In Texas they do, and in a couple of other states they do. But there are energy service providers like WeaveGrid who will offer you a contract, who will say that, or offer your utility a contract and say that, look, we will manage the charging, uh, and per vehicle that you give us access to, this is what we will pay you, and you can share that with the customer or not, and then they'll keep some of that margin for themselves. And so GM actually just signed a deal with WeaveGrid where this control can be exercised through the vehicle software. Of course, it doesn't have to necessarily occur through the utility, and so and the utility can be involved also. So this is happening, and I know sometime last year, if you had an EV in DTE's territory, DTE invited you to kind of sign up with WeaveGrid so that WeaveGrid could watch your EV and could actually learn what the patterns are when people actually charge. So again, a lot of this isn't here yet, but it is also not science fiction, I don't think.
Hey, Ron, you get the last question. Go ahead. Go ahead, Ron. We don't hear you.
Can you hear me now?
Yep.
Jay, I'm loving the hack, by the way. I don't have the courage to do anything like it, but it sounds incredible.
So can you hear me now, John?
Yes, yes.
Okay, so I'm using WeaveGrid for about 3 or 4 years, and I've communicated to them often that we have solar panels and I charge the car when the sun is out. So they don't really handle that situation very well. What they do is they speak to the charger. My
Uh-huh.
my panels are behind the meter. So they'll still throttle me. Like this whole week, they've been throttling me on the charger, even though I'm not actually drawing from DTE. So there's still some things to work out with people who have solar panels. Um, my question
Interesting.
my question is for your second study, what did you assume the penetration of EV use was in the PGM grid area?
So we assumed that it was 10% across PJM. We also modeled the 5 subregions of PJM and modeled transmission constraints between them. And between those 5 subregions, we assumed that the number of EVs available were proportional to the population of those regions.
Okay, thank you.
Well, it's after 8 o'clock. Parth, thank you very much for a great discussion.
Thank you
And
so much.
yeah, thanks for joining us and sharing the information and answering all the questions. And next week we're going to have a member meeting, and John will be sending out a notice to everybody. And so hope to see you next week. And thanks for joining us, and stay cool and keep away from the smoke. Take care, everybody.
Thank you so much. Bye.
Thanks, guys.